So, presentation today, dissecting smart meters. So my name's Justin Searle. I'm a managing partner for a firm in the US called UtiliSec, who specialize in providing security consulting services for the energy sector, both for utilities as well as for vendors that are selling to many of the utilities that are out there. Our services include, besides doing penetration testing, which is some of the efforts that I lead, we also do security reviews with them. We also will sit down with the electric utilities and help them design security programs, get their organizations up and running, because a lot of times, a lot of the electric utilities traditionally have been organizations that haven't really needed or thought they've needed a lot of security inside of their organizations. And when they do, it's usually more on the IT corporate side of the house and not necessarily the critical infrastructure side of the house, because their critical infrastructure was always kind of segmented off, separated out from the rest of the IT world. So now with this new thing called smart grid, where we're having all these new communications and new interdependencies upon all the different systems, it's really taking that control system world that was traditionally isolated and in many cases air-gapped, and starting to throw them together with IT, having a lot of our control systems having dependencies with our traditional IT systems. And all of us have seen over the news over the last 5-10 years how many critical infrastructure systems keep on getting exposed to the internet. A lot of this is because a lot of the people controlling these critical infrastructure system, it's new to them. This whole concept of connectivity and security and not having to worry about the physical boundaries anymore. So when the utilities often introduce security, in many cases, not always, in many cases, the people that are trying to do security are the control engineers themselves that actually operate the equipment, that don't have a security background, and usually in most cases don't have an IT background at all. So it's been a very, very uphill battle for the energy sector for many years now, and will continue to be. But just like any sector, they're growing. We're working together, and that's one thing that UtiliSec really tries to do with them. So we also do different types of training sessions with them. We have people on our team that will help with policy. I personally will push that off all the time, right? That's when you're a pen tester, you always try to stay away from the paperwork as much as possible, minus the report, which you can never get around. So UtiliSec, what do we do? Right now, UtiliSec is doing a lot inside of the energy sector, inside of the U.S. Most of what we're doing in the U.S. centers around some of the Department of Energy initiatives, creating guidance documents for the energy sector. If anybody's ever looked at some of these guidance documents, probably one of the bigger ones being the NIST Interagency Report 7628. That's a document that we were very integrally a part of. In fact, if you ever look at that document, every single diagram inside of that document was actually created by our company, by UtiliSec, by myself and my partner. We do a lot there. A lot of the content that we're going to be talking about today with the penetration testing methodology actually comes directly from this work as well. In fact, the white paper that you all have and have all received on your DVD, conference DVD, actually is one that we created for Department of Energy and one of their government grants out there. And so while we do a lot with the United States and a lot with the guidance there, we do have a few international customers, and we do have some exposure to different international groups, as well as some standards work, because a lot of the standards work that we do inside of the energy sector really is starting to become kind of cooperative efforts between Europe and the US. So there's different security groups in both that in fact, just yesterday we started reviewing some documents that was actually created by a smart grid consortium here in Europe that's been formed and started to produce documentation and guidance documents. So really the purpose of this talk, we're going to be focusing on smart meters themselves. My goal in this talk is to try to enable each one of you for those that have never messed with the energy sector, never done any security work in the energy sector, never touched some of these smart meters and embedded devices. My goal is to try to enable you so that you know exactly where your skills fit. Because at the end of the day, what we're doing inside of energy sector, no matter what people will tell you, and you talk to some of the control engineers that's been in energy sector permanently, they'll say, oh, it's totally different, okay? From somebody that's been on both sides of the fence, the skill set needed to be able to do the security work inside of the energy sector really isn't that much different than we do in all the other verticals. So everybody's skill set in this room applies directly to the energy sector. There's minor differences. You have to think about things in a slightly different paradigm. But at the end of the day, the skill sets are still valid. So really, I'm hopefully going to be able to portray that to you. Another thing that I do in this presentation, as well as most of the energy sector presentations I do to the general security community, is I always try to give a message that's not overhyped. Yes, we have serious issues in the energy sector. I mean, you can see from all the different news media and all the different vulnerabilities and leaks that have come out that we have issues. But name a single sector that doesn't have issues. It's something that everybody's dealing with. You know, specifically with smart meters, I'm really happy where the smart meters currently are today. They're not perfect. There's a lot more work to do. But the security posture for the smart meters themselves actually is fairly decent, especially when you consider it and compare it to some of the other devices inside of the energy sector, like the reclosures and some of the relays and the IEDs that we have, which are the ones that are actually controlling the bulk of the power, the ones that are more sensitive, more critical. Smart meters are actually doing fairly well. So before we get into it and talk about the different tasks we perform in penetration testing and different skill sets, let's go ahead and do a high-level overview of what AMI is. Okay, so inside of the energy world, there's always been electric meters that we've had. Traditionally, they were physical meters that had mechanical devices tracking the power that we were using. About 20 years ago, we started shifting over to more digital devices, and they started calling them AMR readers or meters that as they were tracking your power, in order to facilitate the reading of the meters and not force meter readers to come actually literally to your meter and read it, but they could do it from their car, they had a technology called AMR, where these meters would have broadcast signals. Many of them were actually using a technology that was patented by Itron, called ERT, probably one of the more commonly deployed AMR solutions, at least in the US, and I know they're commonly deployed elsewhere. I can't speak for percentages here across Europe or other parts of the world, but I know for the AMR solution, it was definitely one of the most common solutions we had deployed in the US. Very, very simple broadcast technology. It would actually broadcast out every couple seconds. It would randomly pick one of the 40 different channels that were available between a certain frequency range and just broadcast it out, clear text, no encryption, no nothing. So all the thing we hear about privacy, about being able to read your meters, well, it's actually been an issue that we've had for years. Any electric utility that has meter readers that go through and don't have to physically visit your house and can catch these signals, anybody can capture these signals. You can buy meters online for $100 to be able to go through and catch these ERT signals to be able to see, when a person's not at home, or try to track what types of movies they're watching. You guys have seen the research that just came out a few months ago. Some meters back in the UK that were actually taking 2-second interval reads of the power consumption. We're able to try to fingerprint what movies and shows you were watching on TV. Luckily, most of our smart meters aren't quite that granular, down to the 2-second range. In fact, when we're talking about most of the traditional AMI infrastructure that are being deployed across the world by electric utilities using this meter-to-meter mesh networks, most of those are only reading your power about once every 15 minutes. And sending that data back. And at that interval rate, you can't fingerprint hardly anything. You can tell major appliances when they're coming online and offline, but they have no visibility into the sine waves or anything, which is another way that people have been able to fingerprint devices, see the actual disruption as the device comes online. With the current AMI solution, that's not even possible. But with our older solutions, yeah, you could sit on the side of the street and get meter readings every couple seconds from these ERT meters. So this is the modern day. We've gone from those AMR technologies that broadcast everything out to a bidirectional communication model, where we have meters back inside of our home over here on the left-hand side, either our home, our commercial organizations, or industrial organizations that are connected all the way back to the utilities data center in what we call a head end, the server that actually controls this communication to these meters. In between, there's a whole variety of different ways to be able to communicate. So we see in the meters themselves, we have private-public lease lines is actually one of the valid ways that some of these meters will actually transmit back. This is usually less in residentials and more in some of the industrial centers, where industrial centers that have huge loads of data will have these dedicated links for communications back to the electric utility. More on the residential side, you're going to see one of these 3 top solutions instead for communications. Either a communication over power line that basically uses the signaling over your actual power itself to be able to communicate with other meters inside the neighborhood and to the takeout point to send it back to the utility, or with some of the RF mesh networks, which have become very, very popular now. Most of these running this proprietary 900 megahertz frequency that is unique and different and created for every single one of the AMI vendors, like no consistency at all. Seems like what a lot of the AMI vendors will do will either their own engineer teams or hire a third-party firm to grab a TI or one of the other many chips out there that speak the 900 megahertz frequency. At least in the US is common, like 900. I think they do more of the 800s here in Europe. But they'll build their own baseband, their own signaling, their own meshing technology. So it's all unique for every single AMI vendor that's out there. And then on top of that, they'll stick different types of protocols for communication. So in this diagram, I actually try to name out some of the protocols that you have. So you have lower layers, almost always proprietary. On the upper layers, we have a little bit more consistency. I would say between the major AMI vendors that are commonly deployed in the US, I would say about 50% of them are actually using this ANSI C1222 for the communication protocol. Now, it's a standard protocol, but realize that there's no reference implementation. There's no testing for compatibility, and the types of table data that's going back and forth is referenced differently between each of the vendors. So we have a common protocol, but absolutely zero interoperability between any of the AMI vendors currently, which is always fun. So, and then sometimes you see other different types of combinations using some of the other ANSI C12 protocols that weren't necessarily made for network communications, but encapsulating instead of TCP/IP data or other types of data and sending it back and forth. So that's the mesh networks. And then also we do have a few providers that do a star topology where they're sending it back to a single central point, sending it back out. And more commonly over the last couple of years, we've actually seen AMI vendors starting to put cellular modems in every single meter deployed. So it has a direct link back to the cellular network. So there's no mesh, there's no takeout points. So basically everything's directly connected to the backhaul or to the WAN connection. Beyond the WAN connection, usually they come back up through a number of different ways, either through a cellular provider or sometimes utilities will actually deploy their own RF towers. But ultimately, we do get back to those head ends back in the energy, in the data center for the energy providers themselves. So when we look at these communications, some of the data that we have flowing back and forth is some of the things that we're most interested in as penetration tester, because we want to access that functionality and test that functionality. So we can see some of the very common different types of functions that we have passing back and forth. So we have, of course, routing advertisements anytime there's any type of a meshing network going back and forth, or depending on the network protocol being used, that's very, very centralized between the devices. But most of the information, like the meter registration, any type of the usage data, for how much power you're using, just some of the more sensitive types of functionality, like doing the cryptography keys, or doing any type of the firmware updates or the power disconnect. Okay, so any of the outage and restoration events. These are some of the more sensitive ones that we're always trying to toggle as penetration testers, because at the end of the day, these are meters on the sides of homes recording power. And just accessing that recording, yeah, we can do fraud and lie about our energy rates, but what a lot of people don't know is many utilities actually have algorithms trying to check for this in the back end to detect to see if there's any major shifts or trends of your power that can be consistently mathematically calculated to be able to tell if you're actually pulling some type of a fraud. So that's something that even if we can pull it at the meters, which we can cause frauds by going back through and recalibrating our meters to make them read 10, 5, 15% less than what our actual usage is. That can be caught by the utility themselves just by simple processing back on the back ends themselves. But for us, I think some of the more interesting things are being able to shut down power for people's homes, be able to do that not just for one home, but more homes, a neighborhood, a city. Of course, be able to do it more than one single home. One single home takes one vulnerability to be able to exploit, to be able to cause that happen in one single home. If you want to shut down power for a larger area like a neighborhood or a city, that's usually going to take several different vulnerabilities. You're going to need at least one vulnerability to get in and start causing this to happen on a smaller scale. Then you need to have usually multiple vulnerabilities beyond that to be able to spread that communication between the other meters and be able to pretend to be that head-end device issuing that command, or be able to find some way to manipulate the cryptography of the communications so that you can properly sign all the different disconnect signals and send them out to everybody. So while it's entirely theoretically possible, right? Any functionality built into a system can always be exploited and take advantage of if the right security controls are not in place. It's always very feasible that could happen, and there could be the vulnerability stacked up to do that. luckily, in order to get those vulnerabilities to line up nowadays is actually fairly difficult, unless you can directly attack that head end and seize control over that head end itself. In the meter themselves, one of the things that we do in our penetration tests, besides checking and testing the head end, besides testing all the communications traffic and the wireless traffic, but we also will go through and do penetration testing on the hardware itself and the embedded side. And the reason why we do this is in the IT world, we've always traditionally assumed if you have physical control over an asset, we assume that everything on that asset is compromised. Of course, we have the whole legal thing about data being encrypted, then you have this whole big old gray area about whether it can be broken or not. But with the meters, we will actually go through and test these meters primarily for the purpose not to control the meter or do something with the meter, but we're looking for vulnerabilities in that one single meter that will allow us to exploit other devices without having to have that physical connectivity. For instance, if on this meter I can actually get enough cryptography information and communication stack network protocol information off this one single device to allow me to communicate directly with some of the other meters or directly with the head end, then that's going to now give me a new attack surface and a new attack point to be able to launch. Or if I can find a single key that's been shared across all the meters that happens to be on this one physical meter and I extract that out, now I have an attack and exploit that I can run against everything else. So when we do penetration testing of the firmware of the embedded device itself, that's what we're looking for. We're looking for different types of vulnerabilities that will allow me to spread my control from this one physical device I have physical control over to other devices I don't have physical control over. So let me go through the penetration testing methodology. That's kind of the overview of smart meters and that technology. One of the things that we did and that UtiliSec works with utilities, and hopefully for those of you that do security consulting or inside of the security field that do testing, hopefully a lot of you guys can get into as well, because I can tell you right now there's more work in the energy sector than the people we currently have doing the work in the energy sector. So any of you guys that do work, any security testing, any security architecture review type skills, we need you in the energy sector just as much as you're needed in other fields. So let's try to empower you guys. So this methodology that we've put together really has taken the whole idea and concept of penetration testing and tried to break it down into 55 different succinct tasks to at least try to bring some consistency and to try to bring a more systematic approach to what we're doing as penetration testing. So when we do this, we actually have broken into several different fields. Of course, you have your planning and you have the target setup, and we have the end-to-end summary of reviewing everything, making sure we don't have any gaps in our final report. That's kind of consistent no matter what we do. But when we're testing the smart grid devices and AMI meters, we've broken our document and our methodology into 4 main different sections. So we have our embedded device penetration testing, we have the network communications, we have the server OS penetration testing, and the server application penetration testing tasks. The reason why we broke them into these is these 4 fields represent very, very unique tasks and skill sets when we're dealing with penetration testers. We have penetration testers that work very, very well with web applications and web service, which are the primary applications used on these back-end systems. We have penetration testers that work very well with operating system and traditional network-based assessments. We have real operating systems here running commodity software on commodity hardware, Windows, Linux, Unix. Okay? These skill sets directly apply. So that's one task. Network communications, people that actually have skill sets going in and reverse engineering some of the different communications protocol and analyzing packets that are captured either from the RF or from the wire is one set of tasks that we have. And then finally, the embedded space, where granted, we don't have as many people in the security field that are doing work inside of this space, but hey, it's wide open. It's very, very needed, not just in meters, but elsewhere as well. So you notice also the colors. The colors do have some rhyme and some reason to them. Usually when we're working with electric utilities and vendors, they always want to know, well, what would you recommend? If you want to, give me a recommendation of the types of tasks that we should perform first or more frequently, and what are the types of tasks that, if we have enough budget, would be very, very good to do, but if we don't have enough budget and we have to make a cut somewhere, what should we start cutting out? So this actually breaks down some of those recommendations. Green being, hey, these are the things you absolutely got to check for. I mean, if you're not taking at least a couple hours to checking your operating system and your patch levels, looking to see what services you have running and are exposed, I mean, that's like bare bones simple. So that's what we usually recommend first, then the applications, then the network communications, and then the embedded would be one of the last things we recommend that you may need to drop. Not to say you shouldn't do it, it really needs to happen, but for each and every single utility, each and every single utility probably doesn't need to do an embedded test if the vendor's doing it and at least a handful of other utilities are doing it. The more eyes, the better, but anyway, we have to provide some prioritization. So OS penetration testing. Nothing's different here. Every single person. How many pen testers or security testers we have in the room? Okay, by raising hands. Yeah. Everything you guys do in any other types of system, very, very applicable, very valid here if you ever go up against the AMI system and you're going up against a head end. Okay, those head ends usually are going to be a cluster of different servers. Each one of them have different types of functionality. You'll quite often get some of them running Windows, some of them running Linux, depending on the functionality and the OEMs and the vendors that the AMI vendor chose to partner with. So there's not much difference here, just going through testing your patch level, seeing what services are exposed. It's pretty a straightforward penetration test. What we've done is in the methodology trying to provide guidance to electric utilities that are building security teams that have never done penetration testing for them or trying to evaluate third-party services to make sure they have decent skill sets. We do actually go through and break these different tasks down, and if you can see these tasks, people in the back may have a hard time trying to read these, but they are on your conference CD. Most of these things are going to be very, very familiar to what you have. In fact, this maps fairly well with the PTES, the Penetration Testing Execution Standard, for those that have ever looked at that document. So beyond that, we have the application tests as well. So these are the people that are doing more of the web applications and web services. Almost every single one of these head ends actually has a web-based interface, which is the primary interface for these people to actually go through and control this system. And almost every one of the head ends will be communicating with other servers back in the back-end data center. Quite often these head ends are communicating with distribution management systems and your MDMSs, your meter data management systems, as well as some of these other different devices inside of the infrastructure. The way they communicate with all these other servers is most commonly nowadays using some type of a SOAP web service. Sometimes a RESTful web service, it's kind of less common, but more commonly SOAP. And then every now and again we'll actually see something really strange like RPC services back and forth, but it's not nearly as common. Everybody's kind of standardized on SOAP. So any of your penetration testers with skill sets to be able to test web interfaces and test SOAP services, and once again, skill sets directly applicable here. Some of the things you do have to be extremely careful with is for web pen testers. We all know in web pen testing that if you go through and you start fuzzing all the different tools, or worse, you actually have an automated tool to automatically fuzz everything for you with all your form submissions. We all know that you fuzz a form submission that gets sent back to a database, we start cluttering the database with data. Okay, we all know that if you start fuzzing a form that sends out SMS messages to the IT staff cell phones, that the IT staff phones are going to have this little denial of service when you try sending, 150,000 messages to them in a 5-minute period. These are inconveniences. Okay, they're not very often catastrophic inside of in many of the IT settings we have. We have some IT settings that would be catastrophic, don't get me wrong. But we have to be very careful when we're dealing with critical infrastructure and smart meters because guess how you shut down a meter? A post request. You start fuzzing that post request, shutting down meters, and you start fuzzing the field that actually has all the different homes and all the meter ID numbers on them. You're going to be systematically going through and shutting down meters, toggling through those numbers. So we have to be very, very careful when we're testing these systems, be very, very keen at identifying which pages are going to cause problems, blacklisting those pages, going through and manually testing those pages that are going to be more sensitive in nature, like the disconnects, like the firmware updates. Because we don't want to start randomly sending random firmware updates everywhere. It tends to cause issues. So web server breakdown, when we're testing the web interfaces, the methodology goes through and our penetration testing plans go through and breaks into 3 major categories. This is consistent with the methodology that we teach at SANS. I don't know if you ever take any SANS classes. I also end up teaching the web pen testing course for SANS. So it's consistent with SANS methodology. It's consistent with the classes that we often teach for Black Hat and OWASP for a penetration testing methodology. So 4-step methodology, reconnaissance, mapping, discovery, and exploitation. And if you look at the subtasks, all these subtasks are also consistent with some of the OWASP guidance that are out there, the OWASP penetration testing guide. So you'll be able to see direct one-to-one mappings to that guidance as well. Once again, the work that I try to do, I always try to keep in sync with the rest of us inside a community. We have too many various disparate standards all over the place that aren't related to each other, especially when you start going from country to country, it gets a bit ridiculous. So the more we can bind together, the better off we're going to be. Another thing that we need to pay attention to is cross-site request forgery. Okay, attacks like that, cross-site request forgery, it plagues almost every single application we have. And still today, many testers aren't testing for cross-site request forgery, even though it's trivial to find, and you find it in almost every single app you have. When we get to critical infrastructure, you can actually do a lot of really fun and cool things with cross-site request forgery when you find them, like using your MySpace page to automatically call a shutdown power disconnect for home users 1 through 10,000. If the customer service agent that has access to that interface and is logged in happens to visit your MySpace page, which, oh, by the way, you can usually just call up on the phone and actually try to get them to surf to anywhere that you really want them to surf to. It's trivial. So these types of vulnerabilities are very, very prevalent in these environments as well, just like in any web application. Nothing different here. In fact, since a lot of these head-end devices are not expected to be exposed to the internet, a lot of the due diligence maybe hasn't been done quite yet, or isn't being done as well as some of the other organizations that have web applications exposed to the internet. So lots of right findings to find there. Network communications. When we look at the network communications, quite often we'll break the network communications down into 2 different subtasks. We'll do one that's usually more RF-centric, be able to go back and try to capture packets out of the air, reverse engineer the hopping frequencies that they're using and the modulation that they're using to see if we can create our own traffic or read that traffic out of the air. And then we usually will break it into a separate network protocol analysis as well. Because at the end of the day, I think most of us, when we have RF communications, if we can break the baseband communications, the RF, most of us just assume that that's not where the security is anyway. The security should be in the protocols that are actually passing the data back and forth. So quite often, we'll actually end up skipping the RF packet analysis, unless, of course, you're talking about certain smart grid devices outside of meters, more like sync or phasers, a newer technology that uses GPS signaling to be able to basically timestamp down anywhere from 30 times a second to 240 times per second the actual meter reading. Okay, so sync or phasers are kind of like the oscilloscope of the energy world that are just barely now being deployed, at least commonly to being deployed. So when we look at these different things, you can try the different RF packet tags to them. You can actually try the network traffic tracks. Often when we're dealing with network protocols in AMI, as I mentioned, we usually have a lot of differences and a lot of custom one-off solutions. Either the whole solution is proprietary, or they're using a common standard like C1222, but yet they've implemented it in different ways. It's non-consistent. So we've been trying to do things like getting dissectors to work inside of Wireshark, which, by the way, there is a C1222 dissector available for Wireshark. It is not in the current released version of Wireshark. However, if you dig into the archives, you will find that one of the AMI meter vendors actually submitted a dissector for Wireshark to the project, and over the last year they've been working on trying to get it accepted into the main tree, and unfortunately they haven't had any luck in getting it to accepted. So if any of you guys can pull some strings in the Wireshark project, please go grab the C1222 and actually help us force that into it. We already have it. It currently has the #1 votes out of any other submission inside of the Wireshark project to get accepted to the branch. So if you can help push that along, we'd definitely love it. It would help all of us. So we break these network communications down. As I said, the RF side on the left, we have our network communications on the right. The left side has more to do with capturing the signals, trying to reverse engineer some of the modulations and the frequency hopping, just so we can actually start communicating, sniffing #1, communicating #2. On the right-hand side, we're dealing with the traffic captures. One of the first things that we always do when we do traffic captures inside of AMI or smart grid in general is quite often you find that probably about 50% of the time you're dealing with a protocol you don't have a dissector for. You don't even know what the protocol is because they usually never mention it inside of their specs, and you may or may not have access to the vendor themselves to be able to discuss it with them. So one of the first things we do is we go through and do a cryptographic analysis just to see what the data that we have is, to see if it's encrypted or not. So that's some of the very first tasks we have. If it is encrypted, then we start investigating, see, hey, what can we do to actually to decrypt this? If it's not encrypted, but yet we still can't read it, we can't dissect it or anything, then we can take some time to try to reverse engineer the protocol, try to identify what standard it is, try to write some dissectors and write some different tools for it inside of Scapy or whatever your favorite tool is. So when we do the cryptographic analysis, this is very similar to what we'll do the very first time. We'll go through and we'll actually grab a whole bunch of packet captures of the data. We'll actually strip off all the TCP headers, just get the payloads themselves, and do a statistical analysis of the randomness of that data. So here in the very top one, we can actually see a very good encryption algorithm that's randomly encrypting all that data and has an equal distribution of the randomness across all the different variables inside of the data. And down here on the bottom, this is one that's been encrypted. We can tell it's encrypted because you can see that every single character representation is being represented. They're just not being represented evenly. So we have a little bit of a problem with our cryptography here, which may or may not be something we can take advantage of. Then, of course, if you see something that's not encrypted, you'll just see a big spike right in the middle, right where your common ASCII, printable ASCII characters are, is usually where you'll see that spike, and everything else will be fairly low. So if we do know the protocol itself, almost every single one, since we're dealing with device-to-device communication, especially in AMI, every AMI vendor always touts, hey, we have AES encryption going on. That's how they secure their protocol. It's kind of like the web world where websites will say, hey, I'm secure because I use HTTPS. So we get the same thing in the embedded world. Hey, we're secure because we use AES. And then you start asking, okay, well, what about cipher modes? What cipher modes do you use? How do you store your keys? How do you update the keys? And that's usually where you're finding a lot of the flaws. So this is just a very example of being able to prove, hey, we had a vendor that used CTR mode. And if they're using CTR mode, it's okay, well, look, if I can get one single pair of packets that I know what it was encrypted, or know the plain text, I know the encrypted value, a very simple algorithm written into a very simple script can go through and systematically decrypt everything as long as I have consistent consecutive packet captures. So, and then we get to the embedded. Some of the different tasks that we do in the embedded. When we get to the embedded, we'll spend a little bit more time here. In fact, I have a demo of some of the tools that we use while we're doing this. In the embedded space, we'll break it into three different sections. We'll break it into more of the electronic component analysis, which is one of the most common things we do when they choose to do an embedded. Just trying to see what type of data is there, trying to identify different cryptographic keys or firmware devices that they have stored, anything that could be sensitive and easily pulled off of the hardware itself. The field technician interface analysis, this is dealing with the field interface. Most of these devices will have some type of an interface on them when you talk about any type of embedded device deployed in the smart grid. For smart grid specifically, there's an optical interface that's on the front of the meter. If you ever see a smart grid, you usually see this little round device that has a flat edge with two little what look like LEDs in there. They're actually optical transmitters that are inside of there, so you can actually communicate back and forth. In fact, I did happen to actually bring my portable hardware tech kit. This is what the readers will look like for the optical interfaces. So this whole series of tasks with the field technician interface usually deals with trying to take advantage of that interface, going through and trying to either brute force the key themselves, or if we grab the key through some other method, like through grabbing it off one of the EEPROMs or the flash devices, now we have a password for that interface, connect to that interface and see how much of the data we can actually read off of it. Because on that optical interface, many times you can do everything, including reflash that device itself. So as long as you grab the right password, that's the master password, the greater password, because there's different levels inside of most of these smart meters. Quite often you can actually go through and grab the majority of the data on the meter and even modify and change the majority of the data on that meter themselves. This is something that's sometimes a big surprise to the electric utility, because the electric utility is given tools by the vendor. They're given these same exact readers, and they're giving a piece of software that has a very limited set of functionality to them. And often the utility doesn't even realize that, hey, you can actually do almost anything you want to this meter through this optical interface. It's not 100% true, but you do get a lot more functionality than what the utilities are ever permitted to gain access to. In fact, did you guys hear on the ShmooCon? There was an individual, Don Weber from InGuardians, was going to be releasing a tool, and his talk got pulled from ShmooCon this January. He was actually releasing a tool to use this to be able to interface with the meter. That was a tool that got blocked. Luckily, that hopefully will be released here soon. This is a tool that Don was really trying to release to the public and give and empower the electric utilities to do their own security testing and give them this great utility that's not only for or security testing. They could even take this tool, because it's a general purpose C1218 protocol tool, which is the protocol this optical interface reads. It's a general tool that the utility could take, since it's open source, and repurpose it for their own business purposes. It's something that would provide value for every single electric utility out there and every single security firm out there trying to do testing for the electric utilities. So it's absolutely ridiculous that it was being stopped. There's no exploits in there. He wasn't revealing any vulnerabilities. He was trying to actually give a tool to the security community and the electric utility community to empower them and actually have greater ability to test these interfaces. So unfortunately, it was pretty sad. Luckily, I think they've been able to work through the majority of those issues, and we should have that tool released here to us in the next few weeks. And then finally, the firmware binary analysis. One of the things that we're often trying to do in our test is try to gather the firmware itself. And if we gather the firmware itself, you can go through and do a binary, reversing the binary and do testing of the binary. Of course, we have a lot of utilities that opt not to do that, and we actually recommend budgetary-wise to save that as very last, because at the end of the day, you might find some really good things, but anybody that's reverse engineered binary versions, it's a very, very time-intensive process to try to do that. So here's a breakdown of each one of those three major categories. So you can see over there on the left-hand side, the device disassembly when we're dealing with the electrical components. Disassembling a device, doing the circuit analysis, so actually going in, trying to identify every single chip that's on the board. And then after we identify the chips, we go through and grab the data sheets for each one of those chips and start looking at functionality of the chips. Primarily, we're looking for if that device, that component actually has any type of electrical storage on it. If it does have storage on it, how do we interface with it? Does it have a security bit that prevents me from reading that data once it's been set without resetting the whole chip? So just really looking to see what types of capabilities it has. Also identifying the communications between each of the chips and seeing, hey, is this an I2C bus? Is this an SPI bus? Trying to see how we can actually control each of these different components. So once we have that, we've analyzed the data sheets and we have a little better idea of what the attack surface is, where we can start looking for data and interfacing with these chips. Then we'll go through and we'll try to go through and do a data dump of the chips on anything that's readable. We'll also go through and do bus sniffing on any of the devices that are communicating with each other. So say you have a microprocessor talking to an RF chip. Okay, sniff the data right there, especially upon boot up, because sometimes there's going to be a key exchange that's being passed back and forth between those devices. Or say you have some protected storage over here in a microprocessor. Sometimes they'll actually be pulling data out of that in an unprotected manner, and you can capture it as it's floating between those devices. So we'll try to gather as much of this data as we possibly can, straight from the chips as well as from the bus. And at that point, we're not trying to reverse engineer it. We're trying to just gather this data so we can start doing some analysis of it. Once we have this data, some of the analysis we do is we'll do strings analysis on these chips, trying to identify if there's anything human readable on there. A lot of these devices will have at least one of their passwords. On an average smart meter, I would say that there's probably 10 to 15, sometimes as many as 20 different passwords for different purposes on these meters. So we'll often try to identify one of those passwords that we can possibly gather from either the dumped storage or from the stuff we captured online. We do that by looking at strings, because if it's user set, usually it's something that's very, very readable. And yes, they make the same mistakes in the energy sector as we'd make in IT. They'll name it after the vendor, or they'll name it after the person deploying it, or the company that purchased the meters. We've seen things like that. Luckily, it's getting better, not as common. We'll also go through, and if they're doing asymmetrical keys or they're randomly choosing their keys, we'll go through and do an entropy analysis trying to identify where those keys are and fingerprint where they are. And then if worse comes to worse, if we have a tool for whatever protocol the key's used in, we can sit there and have a tool that we have, or write a tool that will systematically try to go through and every single possible combination of data from what we've captured, use that as valid key material. So, and then we'll do some things very, very similar on the interface, try to capture the communication interface, try to recreate the interfaces to be able to go through and be able to fuzz each one of the endpoints, or just simply try to extract data out that's not exposed normally. So as I mentioned, when we're actually getting this data off these chips themselves, two types of data we're looking for: data at rest, which is usually stored on the flash or the EEPROMs, or data in motion that's literally being passed between the chips on the embedded boards themselves. You can get any type of data here. We're never trying to reverse engineer all this types of communication back and forth. Often we're dealing with the data and we have no clue what all the different pieces are. But what we are usually looking for is we're looking for keys that can be used, or we're looking for the firmware. Once again, in penetration testing, we always have limited time, limited scope. So this is our first pass. We'd love it if they would pay us to go through and reverse engineer everything. Unfortunately, that's not usually the case. So let's try to go as deep as we can in as limited time as we possibly can. So here's an example of just going through and interfacing with an IC. This was more of a permanent board that we were doing some testing on. So we actually literally soldered wires onto this board itself. But quite often, what we're usually using is we have these little micro clips. They work really, really good with surface mount devices. Be able to go in and clip right on the little teeny leads of surface mount devices. Everything down to the smallest surface mounts, they work very good. When you get to the smallest ones, these ones, they actually have one smaller set than these, but I'm not a big fan of them. They tend to be more problematic and astronomically priced more than anything. So you'll also see on this left-hand side that what looks like a wire, it's actually a syringe, a needle that's going in. When you're dealing with some of these devices, the pins are so small, quite often we'll actually use a syringe to be able to pinpoint, because traditional electronic leads are simply too big. So if you simply get a nice big syringe, like big giant, like heroin syringe is what most people will call them, because they're so large. Those actually work very, very well. In fact, for some reason, you know how stringent they are inside the United States about laws on what you can and can't. I can't take a water bottle with me, but TSA has never actually stopped me from carrying 5 of these big old giant syringes with me. Go figure. And they've spotted. They've seen them. They've taken apart my kits before, and they're always more concerned about the pair of pliers that's sitting in the bin next to them instead of the syringes. I just don't get it. So syringes work really, really well when you're trying to pinpoint things. Every now and again, when you're trying to control a chip themselves, sometimes you have other chips that are getting in the way. One microprocessor that's controlling your EEPROM or your flash. Often there's a reset pin. You can just go ahead and tie it to high or low depending on the chip's needs to be able to disable the chip. Sometimes you have to do something more. This is an example of actually simply lifting a pin to be able to stop that communication from interrupting what we're trying to do. Okay, when we're interfacing with the EEPROMs and the flash devices, we're usually using specialized tools to do this. You can use something like the Bus Pirate, okay, open source hardware project, fairly cheap. In fact, here's my Bus Pirate right here. But quite often, usually when we're doing our testing, we are using more devices from what like TotalFace uses. Okay, so the Aardvark and the Beagle device for being able to sniff the communications and the devices off the interfaces themselves. So this actually is a screenshot of using one of the Aardvark devices interfacing with one of the chips themselves. And you can see down here all the data that's coming back off the chip. So here's an example of doing the bus snooping. Okay, so using something like the Beagle to go through and capture the communications like the I2C or the SPI communications on the device. You can see that once again the syringe is being used to be able to pinpoint the 2 pins that we actually want to sniff data off. And this is just a dump of the data itself. So once again, we're trying to use this, trying to identify the keys inside of this raw data dump. Once we have the data, either from the data at rest or the data in motion, depending on how we gather that data, as I mentioned, the first thing that we usually do is go through and start doing searches, trying to identify those keys. If we can't find them in a strings-based manner, then we'll go through and start doing a entropy analysis test, trying to identify them. If we can't find them that way, then we can go through and do something like this, which is more of a systematic approach. So very similar to how they were able to first crack HD DVD and your Blu-ray devices. They went into a player that was running inside of Windows, captured the RAM back out of there, and then systematically wrote a tool to step through every single possible combination, trying that as the possible key to decrypt the data. We do the same exact thing here. So this is actually an example with Zigbee, and I'll actually run this demo here in just a few minutes for you. But it tries every single possible combination from a RAM dump from one of the chips as possible key material to decrypt the data. So as long as we have an encrypted packet and we know what that's supposed to look like, which is fairly easy in Zigbee because there's some known identifiers, we can attempt to decrypt that data. Okay? And this is an example of the entropy analysis. So once we have that data set, we can go through and do that entropy analysis. And anytime we start looking at the random data and we see a large spike like right here, okay, in this scenario, this was the asymmetrical key that was actually hidden inside of this data dump. Okay? So asymmetrical, we love asymmetrical, right? It's really easy to update. Unfortunately, it's very, very easy to spot in a whole bunch of data that's not random just by using this method. So it makes it very, very quick to find some of the asymmetrical keys. Now let me go through and show you some of these things. Now I did not bring a meter with us. Unfortunately, a lot of the AMI vendors are not necessarily wanting to be known or publicized. But the AMI vendors are very, very good to work with. I recommend if any of you ever do any security testing with any of the AMI vendors, get in touch with the security teams. Usually they're very, very helpful to be able to communicate with them. They've gone through the processes enough with penetration testing teams that they now no longer, most of them no longer will try to hide their information from you or try to stop you. Most of them are very, very good. In fact, many of the AMI vendors will actually come right up and say, hey, yeah, these are the vulnerabilities we've had, these are the ones we've addressed, these are the ones that are still open. So they're getting very, very good at this process. All right. So what I would have done is actually bring the meter so we could actually dump some of the information off, which would have been kind of fun to do. But anyway, so what I have here, let me show you right here, is I actually have two different files. So I have a mem dump, which is actually going to be some data that we'd actually pulled off of a RAM on one of the chips that was communicating with a Zigbee communications protocol. And we also have a capture of the Zigbee traffic. Okay, now this example is just for Zigbee, and this tool only works with Zigbee. But once again, you can use the same exact mechanism with any protocol that you have. You just have to be able to write your own script to be able to try to decrypt it, and you have to be able to feed the key in, the possible key in, systematically step through the different data, and then you have to have some identifier to validate that, yes, I would successfully decrypted this data properly, or validated the key signature if it's not encrypted and just signed. So these are the two different values that are here. So when I have that mem dump, usually the first thing that I'm going to do is I want to go ahead and just look at that mem dump to see what I have, see if there's anything I can spot out of it. Sometimes you'll see copyright information, sometimes you'll see other types of plain text information coming back up. So this is just using hex dump. You can use whatever tool you prefer to use to go through and look at the binaries. So but there's really not that much here, and you can see that for the most part, we can't really identify anything that's here. Of course, this is only using one different type of encoding method. You can go through and try Unicode, try ASCII, try various different types of methods to see if anything happens to come out of this data set. We can also then go through and do something like a strings dump, okay, to be able to identify if there's anything coming out of this. It might be a little easier to identify this than in looking at the raw dump itself. So sometimes as you're going through, you'll actually see things just totally jump out at you. And there was one time that we were doing a test where the name of the utility actually jumped right out at us. And it's like, okay, well, that's rather interesting. And it ended up happening to be the key, or at least part of the key. Because it was non-standard. It's not something, you don't expect, you expect to see something related to the AMI vendor that's in there, because they'll have a copyright or something that's usually that comes through via ASCII. But you don't really expect to see their customer's name located inside of here all that frequently. So after we go through and do that, we try to see if there's anything there. We can run that statistical analysis tool to see if there's any randomness on that. And if that doesn't work, then once again, we can always resort to that brute force method, trying every single combination of possible key inputs. So this is the tool for doing it with Zigbee. This is part of Killer Bee. Have any of you guys ever messed around with Killer Bee before? Okay, be able to pen test Zigbee devices. Great project written by Joshua Wright. If you ever want to play around with Zigbee, it's one of the only tools that's out there to be able to go through and do packet captures and put it not just to capture, but actually get it into a PCAP file, something that we all have tools to mess with. Because if you ever get a commercial product to sniff Zigbee, they always use a different non-PCAP file to be able to do this. So Killer Bee will actually capture things inside of PCAPs for you. It will do transposing back and forth between the most common commercial product out there, as well as give you interface interfaces inside of the ZigBee protocol to be able to go through and inject your own packets inside of ZigBee. So it's a really, really great project for playing with ZigBee. So here's ZigBee GoodFind. One of the tools that's in there that will literally do that, trying to find the key inside of a memory dump, trying to decrypt a ZigBee packet. So all I'm doing is I'm passing it an encrypted sample of the data that I captured off of using Killer Bee's tools and Killer Bee's hardware to capture the encrypted ZigBee communications. And then I have my mem dump that I went through and can use aardvark for to be able to capture right back off of the chip. Now in this example, it's a dump of RAM from a vulnerability that we had in one of the chips where it had a security bit set on the chip. And when you hit that security bit, it dumped everything inside of the storage of the chip except for its RAM. And we were able to go in and strip back out the RAM. That was actually using a GoodFet device to go through and launch that specific attack. But you can use like the aardvark or the bus pirate to grab information from your EEPROMs and your flashes and do the same exact attack on those devices as well, if they have ZigBee stored on them, or if you're trying to attack the C1218 password for the optical interface, do the same exact thing there to systematically step through it, which, by the way, is one of the attacks that's actually built into Don Weber's tool, which will hopefully be launched here soon. Okay, so all we do is we run this. It's using that same exact file, that memdump file that we stepped through, tried every single possibility, and it found on guess number 6,264 that this exact string set happened to be the one that went through and decrypted the ZigBee communications. So it was able to successfully identify from that memory dump exactly where the key was and what the valid key was. Okay, so these are the types of things that we're doing in our attacks while we're trying to dump the data off. Another thing that we can do, besides trying to find the key, is we'll also look for the firmware as well. And with the firmware images, sometimes you're looking for simply the file structure names and some of the file headers at the very beginning to be able to identify where the image file is. If we can extract out that image file, then we can go ahead and leverage that for additional attacks. So if we want to try to reverse engineer or do any type of analysis on that binary file itself. Simply for the fact of being able to grab that firmware image usually is a vulnerability in and of itself. And especially if you find a method that not only allows you to capture it, but allows you to go back, turn it back in and change it inside of the device. So anyway, so that is the end of the demo and the end of the presentation. I have contact information. Feel free to use it. And with that, open it up to questions, if anybody has any questions. Told you it was a quiet audience. So if you guys are interested, I am actually in the middle of writing a course, just a 2-day training course for this. We're going to be launching it initially at BrewCon in Belgium, and if it goes well there, we may be coming back and offering it here at Black Hat as well. So just basically a 2-day course that will step through a lot of these same methodologies, these same exact techniques, but actually with real hardware that you can actually play around with. Right now I'm writing the course so that it's not just smart meters, but it will mess with smart meters. It'll play around with home area networks, like some of the ZigBee protocol stuff, as well as PLCs and SCADA communication protocols. So that's what the course is currently turning out to be. And like I said, we're going to do the initial launch at BrewCon in what is it, the first week of October? No, last week of September is going to be BrewCon. We're going to hold it in Ghent. So. All right. Sounds good. Thank you.